Now let us move on to ICSE concept builder example number 10. This is a very important question based on the concept of a meter rule. So meter rules, all the numericals on meter rules are very important from ICSE point of view, right? So please by heart these numericals and practice them pretty well. So this question says that a uniform meter rule has its fulcrum. Pay careful attention. It is given that the fulcrum or the pivot point, the fulcrum is always the point about which the forces act. This is the point of rotation. So a uniform meter rule has its fulcrum placed at its midpoint O. So as shown in the figure, this is the pivot point and the rule balances about this point. Let us call this point O, and it has a weight of 50 kgf. So this rule has a weight of 50 kgf acting in the vertically downward direction at the 20 centimeter mark. So this is the 20 centimeter mark. Now the moment you see the position of this weight at this 20 centimeter mark, what do you understand by this? What does this indicate? It simply indicates that this force is at a perpendicular distance of 50 minus 20, that is 30 centimeters from the central pivot point O. So whenever you consider the moment of this force of 50 kgf, you consider it at a perpendicular distance of 30 centimeters. So that is what it means. And it has another weight of 30 kgf like so at the 90 centimeter mark. This again, what does it indicate? The moment you see a 90 centimeter mark over here, it simply means that this weight of 30 kgf acts at a perpendicular distance of 90 minus 50, which is nothing but 40 centimeters from the central pivot point O. And we are asked, is this rule in an equilibrium position? Now, what is the first thing that we know for an equilibrium position, right? For a meter rule to be horizontal, for it to be in equilibrium, it must be horizontal. And as a result, it must follow the principle of moments. So what does the principle of moments tell us? It says that the clockwise moment about the fulcrum must be equal to the anti-clockwise moment about the fulcrum. Observe, for this force of 50 kgf, it produces an anti-clockwise direction moment as compared to this force of 30 kgf, which produces a clockwise moment with respect to this central pivot point O. So the anti-clockwise moment due to the 50 kgf force must be equal to the clockwise moment about this 30 kgf force. So as a result, we can say W1 into L1 is equal to W2 into L2. W1 we know is 50 kgf. L1 we know is the perpendicular distance, which is nothing but 30 centimeters. W2 again we know the force is 30 kgf, and L2 we've seen is 40 centimeters from the central pivot point O. So 50 into 30 is equal to 30 into 40, but 50 into 30 is nothing but 1500 Newton meter, which is way greater than 30 into 40 is nothing but 1200 Newton meter, right? So this condition is not satisfied, as W1 into L1 is observed to be greater than W2 into L2. What does this imply? It simply implies that this particular scale is not in equilibrium, right? And it will not remain horizontal, because for it to be in equilibrium and to remain horizontal, W1 into L1 must be equal to W2 into L2, which is not the case over here. So as a result, this meter rule would tend to get inclined or tilted in an anti-clockwise direction like so, thanks to the greater anti-clockwise moment. And thus we can say that the rule is not in equilibrium and it will turn anti-clockwise. So that answers the very first part of the question. So we certainly know for sure that the rule is not in equilibrium position. Secondly, we are asked, if not, that means if the rule is not in the equilibrium position, then how can it be brought to an equilibrium position by using another weight of 30 kgf? Obviously, in this case, if the forces are greater this side, as a result of which the rule is getting bent in an anti-clockwise direction like so, we'll require to add another weight on the right hand side so as to balance out the rule by adding a greater force in the clockwise direction like so. And thus we can say that now, to maintain the rule in equilibrium position using an additional weight of 30 kgf, so let L3 be the length at which the additional weight is applied. We don't really know that at what length we need to apply this additional weight of 30 kgf in addition to the existing one, and hence we can say that we know that for the rule to be in equilibrium position it must be horizontal, and at this stage we already know that it is observed that the sum of the clockwise moments must be equal to the sum of the anti-clockwise moments. So the anti-clockwise moment we know in this case is 50 into 30 must be equal to, we've already seen it should be equal to 30 into 40 plus the additional weight that we are talking about, that is 30 kgf, multiplied by certain length L3 at which it should be applied. Now how do you get this equation? Remember, on one side we have all the anti-clockwise moments, and on the other side of the equation we have all the clockwise moments. Now as the additional weight would be added over here in this direction, so as to bring the rule back in equilibrium, this weight has to be applied in the clockwise direction and hence is to be added on the right hand side of this equation. So on one side of the equation we would have all the anti-clockwise moments, and on the other side we should be having all the clockwise moments. So we get a simple equation, 50 into 30 is equal to 30 times 40 plus 30, that is the additional weight times the length L3. As a result we get the length L3 to be 10 centimeters, and thus the additional weight must be applied at a distance of 10 centimeters from the center. The center we know is at O, which is at the 50 centimeter mark. So 50 plus 10, that means at the 60 centimeter mark we should have this additional weight of 30 kgs so as to bring the rule in an equilibrium position. If we remove either one of these weights, the rule would again be inclined in an anti-clockwise direction, as this force, the moment due to this force of 50 kg becomes greater in this case, right? So after adding this weight of 30 kgf at the 60 centimeter mark, the rule comes back to the equilibrium position. So that answers the very 10th ICSE concept builder example. So a very important numerical, always remember that we need to add additional weights in the case of a meter rule if at all it is getting inclined to any one direction like so. So with that, let us take a look at a question straight from ICSE 2011 for worth 4 marks. So notice that this is a very scoring question. The question reads that a uniform meter scale can be balanced at the 70 centimeter mark, right? This is very important. It can be balanced. This is a keyword over here. What does this indicate? It simply means that the word balanced means that it can be pivoted at the 70 centimeter mark when a mass of 0.05 kg is hung from the 94 centimeter mark. So if the meter rule is pivoted at the 70 centimeter mark, this mass of 0.05 kg would be acting at the 94 centimeter mark, and we are asked to draw diagram of this arrangement. So this is how the diagram would appear. Remember, the pivot is represented by a small triangle, right? So this balance point acting at the 70 centimeter mark with the weight of 0.05 kgs acting at the 94 centimeter mark as shown. Secondly, we are asked to find the mass of the meter scale. So we know that we've already seen the mass of the meter scale always acts at the midpoint, that is at the 50 centimeter mark. So if you observe from here, this mass about this pivot point would tend to have a anti-clockwise moment, unlike this weight of 0.05 kg which tends to have a clockwise moment. So to be able to calculate this mass, apply the principle of moments about the 70 centimeter mark or about the pivot point, right? So we get W into this distance being 20 centimeters. So W into 70 minus 50, that is 20, is equal to 0.05, right? So this is the clockwise moment on the left hand side and this is the anti-clockwise moment on the right hand side. So 0.05 times 94 minus 70 is nothing but 24. So as a result, the mass of the meter rule becomes W is equal to 0.05 times 24 upon 20, which is nothing but 0.06 kgs. So that's gonna fetch you 4 marks straight away, a very easy concept for one such question asked in ICSE 2011, right? So it is a very coring numerical indeed. So please remember this. Finally, we have a question from ICSE 2014 for 2 marks which says that two forces each of 5 newtons act vertically upwards and downwards respectively on the two ends of a uniform meter rule which is placed at its midpoint as shown, right? So the meter rule is balanced or pivoted at the midpoint as shown, and these two forces of 5 newtons each act at the extreme ends in the vertically upward and the downward direction respectively, and we are asked to determine the magnitude of the resultant moment of these forces about the midpoint.